Okay, in class, we've been looking at different models of the celestial sphere. We had our mental model of us laying in a field and looking at this apparent dome that the sky makes. We've been looking at two-dimensional models that we've drawn, or those examples kind of look like this that are on the Regents questions. Something that is helpful to have you guys understand really what those are showing is to start drawing them for yourselves. So this is a quick kind of review of all the rules that help you to draw one of those. And by going through this set of rules, you're also going to learn a lot of the geometry that relates to different lines and points that are on those, which will help you in the future. Okay, so this is a set of directions. The first thing we need to do is mark the zenith. The zenith is always at 90 degrees of altitude, or 90 degrees off the observer's horizon, or straight up above the observer. Okay, so this is a two-page activity, so you can tear this apart. We're going to do the Schenectady, New York one. First thing we want to do is write in our latitude, 42 degrees north. Okay, there's our little observer, and on here there is an external protractor that goes from 0 to 90, and then from 0 to 90 on this side. 90 is the highest point that we can have, and this is called the zenith. It would be if this observer looks straight up at the highest point on this apparent dome that is representing the sky. The next thing in the directions say to do is mark the altitude of Polaris at that latitude. So Polaris has a relationship with the observer's latitude, and that relationship is that Polaris, or our pole star, which is located over our axis of rotation at 90 degrees north latitude. So when you're standing at the North Pole and you look straight up, you will see Polaris. As you walk towards the equator, Polaris gets lower and lower in the sky until you get to the equator. It will be at the horizon or at 0 degrees altitude. So the altitude of Polaris is equal to the observer's latitude. So at 42 degrees north, Polaris will equal 42 degrees of altitude, or 42 degrees off of the horizon. So the altitude of Polaris is always equal to the observer's latitude when you're in the northern hemisphere. That's because you can't see it in the southern hemisphere. If you're at the equator and it goes to 0, you take one step beyond the equator, it goes below the horizon and you can't see it. So we're going to put Polaris on here. If we're at 42 degrees north, then Polaris will be at 42 degrees. Well, there's a 42 degrees over here, and there's a 42 degrees over here. North is marked here, which makes this south, this west, and this east. We always want to look at our clues to figure out where north, south, east, and west are, whatever we can use. If Polaris, the other name for it, is the North Star, then we want to pick the 42 degrees that's over here, put a little star, and label it Polaris. So that's where Polaris is. Okay, the next thing we want to add in is our equinox line, which is our red line. And here's some things we want to remember. The altitude of the noontime sun on the equinox, both equinoxes, March 21st and September 23rd, is 90 degrees from the altitude of Polaris. The corner of a sheet of paper is also 90 degrees, so you can use it as a reference for 90 degrees. And it explains here how to do that, and I'm going to show you how I do it. I'm going to use my corner of my paper. If you place the actual tip of the paper right at the point where the observer is standing, and you place one side at our 42 degrees where Polaris was, right here, then the other side is 90 degrees away, which is where we want to put a sun. We're going to put a circle right there. That is the altitude of our noontime sun on the equinoxes. So now we know where, so that means this line is due south. So the observer is looking south, and they're going to look at this height, which looks like it's about 45 degrees-ish. Okay? We know on the equinoxes that it says connect the noontime sun to the sunrise and sunset location on the equinoxes. Right away, you should be thinking, okay, on the equinoxes, that's the only day of the year where the sun rises at due east and sets at due west. Okay, so we're going to draw in our sunrise position, due east, sets at due west. There's our sun at different times of day. And we're going to draw it up, curve, and then we're going to dash it back down. We know that going up this curve to noon is the morning, and going back down this way is the afternoon. We'll use this for all sorts of times of day questions, shadow questions, things like that. So in New York State and in the Northern Hemisphere, the sun travels into the southern part of the sky, gets to its highest point at solar noon, which is due south. The observer would look due south, and then it comes back down into the western part of the sky. This is going to be our red equinox line, and it represents March and September. It's 2 days of the year, March 21st, September 21st, or thereabouts, when the equinox occurs. Okay, next we're going to draw our green summer line. The sun will be 23.5 degrees higher in the sky on the summer solstice, which is June 21st. Mark the altitude of the noontime sun on the summer solstice by adding 23.5 degrees to the altitude of the noontime sun on the equinoxes. Okay, we're going to just kind of guess at 23.5 degrees. So you go 20, 10 is here, another 10, and 20. Put us right about here, just below 70. Okay, you're kind of just estimating it. You want it to be about 23.5 degrees higher. We know that relationship, and knowing that will be very helpful. We also know that these paths don't cross each other, and we want a nice long path for the summer. So we know that we don't want to bring the sun down here for sunrise and sunset because they'd be crossing. So they need to remain parallel. So we're going to put our sunrise here and our sunset here and bring it up and bring it down. They should kind of be across from each other. And then we're going to label this line June and color it in green. Okay, so you might want to go back to your paper here and say, on June 21st, the sun will rise slightly. We're in the northern part of the sky, north of east and west, and connect the noontime sun to the sunrise and sunset location. Last line we want to draw is our blue winter line. Mark the sun. The sun will be 23.5 degrees lower on December 21st. You're going to subtract 23.5 degrees this time. And we're going to have our sunrise and sunset is going to be south this time of east and west to remain parallel. And it's going to be blue. So we're going to go lower by 23.5 degrees, roughly. We want our sunrise and sunset to remain here so that they don't cross. It gives us a nice short path, which gives us why we have a 8-hour day or less than 12 here. 12, everybody has 12 on the equinoxes, and then longer or about 16 hours for this one, the duration of the path. It takes the sun longer to travel on the green path. Okay, and this is what it will look like for Schenectady. You guys are going to try some of these other locations and draw them. This one takes you into the southern hemisphere at 23.5 degrees south. So this one, a lot of these other ones are a little tricky because the concept of higher and lower and rising and setting even gets drawn into question. So you kind of have to think about it. You might want to use your paper model of the celestial sphere, the little blue paper model that goes back and forth to help you figure this out. Okay, there is a summary video. Watch it whenever you need to.